This is the second part of section 2.3. We left off with this slide. So as a refresher, the intersection is the elements that they both have, anything that they have in common. And the union is anything that's in A or B or in both sets at the same time. Alright, so find each of the intersections. An intersection is what do they have in common. If you look at the set on the left, this one has A, this one has A, so the intersection, I don't know if I kept saying A, but I meant 8. The intersection would have 8. They both have 10, so that would go in the intersection. And that's it. That's the only thing that they have in common. For the second example, we're looking for what they have in common. This one has all odd numbers, this one has all even numbers. They don't have anything in common. So the intersection would be the empty set. For C, this we have 1, 3, 5, 7, and 9. We want to intersect that with the empty set. Remember, another way of writing the empty set is braces with nothing in the middle. So we look what's inside this set, 1, 3, 5, 7, and 9, to see if it's inside this set. And there's nothing in there, so there is no intersection. The intersection would be the empty set. Find the union. The union, we're going to take this set and this set, and we're going to put them together into one giant set. And if it's a repeat, we don't have to write it twice. So notice this has 8 and this has 8. We don't have to write 2 8s. So we've got a 6, we've got a 7, we've got an 8, we've got a 9, we've got a 10, we've got an 11, and we've got 12. So the union of those two sets, 6, 7, 8, 9, 10, 11, and 12. For the next one, the union, I'm going to take everything in one, everything in the other, put them together into one big set. 1, 2, 3, 4, 5, 6, 7, 8, and 9. For the last one, I have this set, and again, empty set, has nothing in it. So I have to take everything in this one, everything in this one, and add them into one big set. So I have 1, 3, 5, 7, 9. Notice the empty set does not contribute anything to the union. If you have an example like this where it has parentheses, you're always going to perform those first. Anything inside the parentheses gets done first. So for example A, the first thing I want to do is find A union B. So A union B means I want to take both sets. So I want to take both of them together. So I've got 1, I've got 3, I've got 7, I've got 8, 9, and 10. So 1, 3, 7, 8, 9, and 10. That would be the union. Okay, so that is this part of it right here. Working my way out, now I want the complement of this set right here. So that's anything that is outside of this set that's still in the universal set. So 1 is in the union, 3 is in the union, so it's not going to be in the complement, 7 is in the union, 8 is in the union, 9 and 10 are in the union of A and B. So we want anything that would be outside of the union. So anything that's outside. So we have 2, 4, 5, and 6. None of these are in the union. So A union B complement would be 2, 4, 5, and 6. For this example right here, we need to first find A complement, then we have to find B complement, and then we have to find the intersection. So A complement is anything that is in the universal set that is not in A. So if it's in A, we got to cross it out. So 1 is in A, 3, 7, and 9 are all in A. So anything that's outside of A would be 2, 4, 5, 6, 8, and 10. We also have to find the intersection or the complement of B. Sorry, complement of B first. So B complement. So 3 is in B, so we don't want that. We don't want the 7. We don't want the 8. And we don't want the 10. So anything that's outside of that. So we have 1, 2, 4, 5, 6. 1, 2, 4, 5, 6, and 9. And finally, we want the intersection of the two sets that we just found. So the intersection, what do they have in common? A complement intersect B complement. They both have a 2. They both have a 4. They both have a 5. And they both have a 6. Determining sets from a Venn diagram. I'm going to have you write this down. And yes, I know, it's a big long table. I apologize. Set operations and Venn diagrams provide precise ways of organizing, classifying, and describing vast arrays of sets and subsets we encounter every day. Or refers to the union and refers to the intersection. So let's suppose we want to find the cardinal number of the union of two sets. So we have an example here. Some of the results of the campus blood drive indicate that 490 students were willing to donate blood, 340 students were willing to help serve a free breakfast, and 120 students were willing to do both. How many students were willing to donate blood or serve breakfast? Remember, or is the union. So let's first draw a Venn diagram to figure out kind of what the situation is. And when you have the Venn diagram, what you're going to do is you're going to start on the inside and work your way out. In other words, start with who wants to do both. So we had 120 students that were willing to both donate and serve a free breakfast. So that would be in the middle. That would be the intersection. We had 490 students that were willing to donate blood. That includes the 120 students that were willing to do both. So we've got 490 students that were going to give blood, but that includes the 120 students that were willing to do both. So if we just want this area right here that were only willing to give blood and not serve a free breakfast, we would have 370 students that were willing to just give blood. We had 340 students that were willing to serve a free breakfast. Again, that includes the 120 students that were willing to do both. So we have 340 students minus the 120 students that we've already indicated in our Venn diagram. So we have 220 students that were only willing to serve breakfast. Now, to figure out donate or serve, we need this number, and this number. 370 were willing to donate, 120 did both, and 220 for the breakfast. So altogether, we've got 710 that were willing to either donate or give blood, or serve breakfast, or do both. Now, without going to the trouble of doing a Venn diagram, you can get the same answer. We have the blood donors, we have the breakfast servers, but these two numbers have the willing to do both, and we've got it twice. So, to get an actual number, an actual count, we do the blood donors plus the breakfast servers, but we have to take off one of the 120s. So notice we only added on one of the 120s, but we took off two. So to avoid the duplicate, we have to take off one of those intersections. Gives us 710 people who were willing to donate or serve breakfast. The homework is 4 through 96 every 4, 110 through 116 even.